So it's my pleasure to introduce Raghav Jha. He's working at Jefferson Lab in USA. Raghav actually did it masters from St. Xavier's College in Calcutta, and then he went to Syracuse University and did his PhD under Simon Catterall, and then he went to Perimeter Institute. He was there for 3 years. He recently joined in Jefferson Lab and working there in their quantum computing group. So I requested Raghav to give a talk on this, on some recent review article, and he agreed. Then the timing was that Raghav preferred actually these timings, though it is 5:30 in the morning. So thanks, Raghav, for agreeing to give this talk, and you can start now.
Okay, thank you so much, Nilmani, for the introduction and for inviting me to give a talk. This talk will be different from the talks I usually give because I won't be presenting any of the research-related work. It will mostly be just introducing and sort of talking about why people are getting interested into quantum computing and what it can do for physicists and how we can solve different sort of problems, which is not accessible using other methods which we know of today. So it will mostly be some basic review. I will also do a little hands-on thing. I'll show you a couple of things just to get you more feel of what we do in these sort of things, because that will like get you started. If you want to do something on your own, will help you pass that threshold. Okay, so the talk is available online. If you find something interesting in this talk, you can always go back to this link and check it. So this is based on this review article I wrote, after which Nilmani invited me to give a talk at TIFR. So I'm thankful to him. So let me just start with mentioning the outline of my presentation. So I'll talk about what is the state of the art classical methods or the classical computing methods which we use today to understand quantum anybody. And those are called tensor network methods. And then I'll talk about why do we really need quantum computation. So what are the limitations of tensor networks and why do they not work well for some of the problems which we want to study in physics. Then I'll talk about definitions of qubits, qudits, and q-modes. So maybe you're familiar with qubits, but not with qudits and q-modes. I'll just tell you what those are. Those are just generalization of qubits in some sense. And then I will talk about quantum gates, which are unitary gates with which we implement, say, for example, unitary time evolution of the quantum system. And I'll show you some basic demonstration using a software package, which is called Qiskit, which is developed by IBM. And this is like a simulator to do the real quantum computer. So for example, if you have a quantum computer in which you want to compute, rather than just doing it on a physical quantum computer, you can do some sort of a simulator. This is sort of what airline pilots do when they want to train. They use a simulator. So that is what Qiskit is basically. Then I'll talk about a classical quantum hybrid algorithm, which is known as variational quantum eigensolver, and show you an example for a very simple system, an harmonic oscillator, and then also show you some recent work done by other groups on studying the two-dimensional nonlinear sigma model, O3 model, with these qubits. And then I'll show you how we can do time evolution using very basic Hamiltonian. Suppose I give you a Hamiltonian in terms of Pauli matrices. How can I implement the time evolution? So I'll show you an example of that. And then I'll introduce something which I have been recently working on, which is the Q-modes aspect, which is the continuous variable approach to quantum computing. And I'll show you some work which was done by other groups on Bose-Hubbard model using SF simulators. So SF simulator is just a simulator which is called Strawberry Fields simulator. It is developed by a Canadian company, Xanadu. So it's very, so as Qiskit is a qubit a qubit simulator, Strawberry Fields is a photonic simulator in the sense that we deal with harmonic oscillators, quantum harmonic oscillators, and those are what Q modes are basically. So it's sort of analog quantum computation, and Qiskit is like a digital version of that. And I'll then conclude, give some conclusions. Okay, so as I mentioned before, what is the state of the art which we know right now in tensor network numerical quantum many-body systems approach. There are two versions. One is the Hamiltonian version, one is the Lagrangian version. The Hamiltonian version is basically the idea that suppose we have some given quantum system, it's almost impossible, it's not possible to really write down the ground state exactly. So what do? We want to approximate this ground state given by psi, which depends on 2 to the n parameters, by some approximation which is just order n, right? So we want to come up with some method in which we faithfully represent the ground state using order n parameters, and those are called matrix product states. And they have been very successful following the idea of DMRG and matrix product states. So these are the things which people use these days to understand any quantum system. So that is the Hamiltonian version, but this is also a Lagrangian version, which I have been involved with over the last couple of years. And that is more natural to lattice field theorists in the sense that what you have actually is a partition function. And what you really want to do with tensor networks is you want to approximate the partition function. And then you want to start with that initial representation of the Boltzmann weights or the action e to the minus s in terms of tensor networks. And then you perform some sort of a recursive coarse graining scheme based on the singular value decomposition of matrices. And then you generate the fixed point in the thermodynamic limit, and you can study the system. One of the advantages is that you can have that direct access to the partition function. So that is the Lagrangian approach. And I have worked on this because this is promising because, for example, you can do lattice field theory for models where you have sign problems. So it's like an alternative to Monte Carlo method. So that is what tensor network Lagrangian approach. We call it tensor renormalization group, TRG. So these are the classical methods. But before going that, let me just say, why do we really need tensors? So tensors are now basically we are sure that it's one of the most powerful methods known to study any lower dimensional critical or gapped system than any other numerical method available today. For example, I can solve two-dimensional Ising model on Sagar solution in 10 seconds at some fixed temperature, and that is not possible with any other state-of-the-art method, for example. Now, the second advantage, which is more important, is that, as I already mentioned, we can study models where, say, for example, finite density, we have finite chemical potential, or we have a topological theta term. These terms are not possible to study using Monte Carlo methods because of well-known sign problem, etc. So tensor networks have potential to help us in studying these models. But this has only been achieved till now in, say, 2 Euclidean dimension, maybe 3 Euclidean dimension, not in 4 dimension, because it's hard even for tensor networks to go to 4 dimensions. And description in terms of quantum state, in terms of, say, as I mentioned, matrix product state, which is an approximation of the ground state wave function, can help us really understand the real-time dynamics of a quantum system, which is a very important problem. For example, if I take a Ising spin and I tune very close to criticality, and I prepare my ground state in terms of matrix product state, then maybe if I play around with that, it can give me a field theory description, and it can help me understand the real-time evolution of, say, Ising field theory, which is a field theory description of Ising model at close to the critical point, which is known to be an integrable field theory. So these sort of things are interesting for tensor methods, numerical methods. And as is also very well known, tensor networks have some sort of role to play in the emergence of space-time via the famous duality, for example, ADS-Mera, and there have been various proposals after that, in the sense that the critical spin chain on the boundary, as you do the coarse graining or you generate the RG direction, you go in the bulk, and it seems like a tessellation of some time slice of ADS. So tensor and quantum many-body system will have a lot of interesting applications. So I mentioned about matrix product states. This is just a diagrammatic representation of that. On the top, you see a state which is really psi, which has physical indices I1 going through I5. So for example, if it's a spin half system, all of these go from 0 to 1. So these are two, they can have two values, all the I1 through IN. But the basic idea is to represent this psi by some approximate psi, which is mentioned below, by combining rank 3 tensors side by side. And those rank 3 tensors, as you see, is A. The physical index remains the same because we don't want to touch that, which is I1 going through I1 to N. But there are some dummy indices which are known as bond dimension, which are chi0 through chi5, and they represent how the one tensor is connected to the other tensor. So what we really do in this case is that this can faithfully represent the ground state of a local Hamiltonian, because you don't consider the interaction between, say, the spin at site 1 through N. You only consider up to some range. It cannot propagate all the way. And that really cuts down on the number of parameters you need. So that is what the basic idea of MPS is. And then you do some sort of a loss function optimization to tune all these A's such that they give a minimum energy. And that is the psi approximation. So that is what MPS is in very short words. And that is what the Hamiltonian formulation of tensor networks are. In the Lagrangian formulation, as I mentioned, I can compute the partition function. And from the partition function, I can easily compute the free energy. This is the free energy given by Onsager from 1944. And if I plot that, I see that the tensor renormalization group produces this plot in 15 seconds. And I get exactly the same free energy up to 10 to the minus 7 or 10 to the minus 8 in the thermodynamic limit. So this is a very powerful method. So on the both fronts, from the Hamiltonian perspective and even from the Lagrangian perspective. But if everything was all right, we would be happy and not think about anything else. But obviously there's a problem. There's a problem because we cannot go to higher dimensions. For example, using tensor networks, something like MPS in higher dimension is a very problem, is not well-known in general, in the sense that we cannot understand how these things work in, say, 2+1 or 3+1 dimensions. And for example, that leads us to the problem that time evolution of QFT is still a very open problem. We don't really understand, we really don't have tools to understand aspects of time evolution of interacting field theories using any method available. MPS can obviously be useful for 1D quantum, but not in higher dimension. There are some higher dimensional versions of MPS, but they don't work as well. And this all leads us, the problem of scalability of these problems lead us to the quote of Feynman, where he said that nature at its fundamental level is quantum mechanical. So even if you come up with very ingenious classical algorithms, at some point, you will definitely run out of steam because you just cannot do any better than that. So all these methods like DMRG, MPS, they are very interesting. We can study a huge dimension of Hilbert space using classical method, which was like not possible before the 90s. But even then, there's some sort of a limitation, and that leads us to understanding of something other than the classical computing methods. And that is where the motivation for physicists come. We want to solve problems in higher dimension, 3 and 4 dimensions, for example, but we have to start somewhere. And that is what people in the 70s and 80s started thinking about doing computation with a reversible machine based on the principles like superposition and entanglement. How can we make use of these principles to construct a machine or do computation based on this? And this is a famous article by Feynman from, I think, 86, based on some of the talks he had given earlier. And here he is talking about this last paragraph. If you see last paragraph, he talks about these gates, which are control knot and Toffoli and other gates, which is what we'll talk about now in the next couple of slides, because those are the basic building blocks of quantum computers, in the sense that when we think about a laptop or a classical computer, we think about transistors, we think about classical Boolean algebra, AND gate, OR gate, and things like that. But when we go to quantum, everything is a unitary gate. Everything has to be reversible. So we'll try to construct some, introduce unitary gates which are used in quantum computation. So there are two approaches in general to quantum computation. One is the more well-known digital quantum methods, which makes use of qubits to perform computations. There are 3 steps in general. the initial state preparation, and then implementing the unitary time evolution using quantum gates, unitary quantum gates, and then measuring whatever we want to measure in physics, for example. There's an equivalent or similar version using continuous variable quantum computation, where instead of a two-dimensional local Hilbert space of a spin half particle, we use a harmonic oscillator which has infinite Hilbert space. And we use the continuous variables, in fact, the quadratures and x and p's of harmonic oscillator to do the same sort of calculations as we do in digital quantum computing. So these are different approaches. Okay, so I talked about qubits, and Q modes. So in general, qubits is a local Hilbert space T2. So there's 0 and 1. Qubits is D greater than 2. Say, for example, psi can be written as alpha times 0 plus beta times 1 plus gamma times 2, and normalize in the usual sense. And Q modes in general have an infinite dimensional Hilbert space, which is like the quantum harmonic oscillator, which is what also will bring us towards the end of this talk to the idea of the photonic quantum computation, because these photons can be represented by harmonic oscillators. And when we manipulate photons or use photons to perform computations, that is exactly what Q modes are, or for example, analog quantum computing is. Or if we are just using qubits, then we're just using some two-state system, for example. Any qubit, for example, psi, can be represented on this block sphere because of the well-known mapping between SU2 and O3. So it's like on this Riemann sphere, we can represent the states using a qubit. So for example, 0 and 1 are represented here. Those are the North Pole and the South Pole. And then you have some other points, which is plus and minus. I'll show you how we get plus and minus starting from these 0 and 1 states. And you can represent the states using this block sphere. So this is just a representation for the qubits. Okay, so now once we have this, we'll restrict ourselves for the moment to this qubits formulation of quantum computation, approach to quantum computation. And for that, what we really need is to introduce some sort of gates. So for example, gates are something. So for example, if the input state is 0 or 1, gates are unitary transformation which transform those states. Say, for example, if I take a 0, which is shown here, and then I pass it through a gate which is called H. H is just known as the Hadamard gate. If it passes through H, it gives me a state which is plus, and plus is defined like this: 1 over root 2 times 0 plus 1. So it's a uniform superposition state. So if I pass as a 0 state through Hadamard gate, it creates a uniform superposition. And similarly, we have different gates called X, Y, Z. These are just the Pauli gates. So for example, these are the matrix representation, 2 by 2 matrix representation. So 0 passing through X gate will give 1, 1 through Z will give -1, and so on. So these gates, all these gates you see is one qubit gate. And that is why they are 2 by 2 matrices. They can be represented by 2 by 2 matrices. And how do we know it's one qubit? It's just one qubit because there's just one wire here. There's single wire. All the gates have single wires, but there can be gates made up of 2 wires, 2 qubit gates, 3 qubit gates, and things like that. So then 2 qubit gates will be represented by a 4 by 4 matrix, 3 by 8 by 8, and so on. And the plus state is just given by this. So this is just some basic gates. They are all unitary. And okay, once I mentioned this, let me just do a small recap, like do a parallel of classical and quantum. So in classical Boolean algebra, if we have an AND gate and the inputs are 0, 0, we get this. We can have AND gate, OR gate, or XOR gate. So in these cases, the truth table is given by this, and this is all Boolean algebra. For quantum mechanics, it's obviously different because not all of these gates are reversible, in the sense that if I tell you that I pass something through AND gate and I get a 0, you can never construct the input, because 0, 0, 0, 1, and 1, 0 all give you a 0. So there's a loss of information. That never happens for a quantum gate. Quantum gate always have the same number of inputs and outputs, as is seen here. So if I have equivalent version of this in quantum sense, so 0, 0 will give me 0, 0, 0, 1, 0, 1. 1 0 1 1, and 1 1 will give 1 0. Now, important thing to see that is that there's an output gate which is just repeated. So the input is A and B, and output is A, and A O plus B. And this A is just repeated because we want to reproduce the entire input, because we want it to be reversible, and this is what a reversible computing machine needs to do. It cannot use this. It has to use something which has same number of inputs and outputs, so we can always go back. And this gate, is represented in a diagrammatic notation, for example, like this. So if we have two gates, so this is one C0 gate. This is known as one C0 gate or CX gate. We'll come to this in more detail later on. And in the diagram below, I've shown two C0 gates. So one blob with a 1 O plus is one C0 gate. And there is a C0 gate representation in terms of the outer product of the states given by this. So it's called controlled NOT or controlled X. It's called controlled because the first index controls the output. So for example, if A is 0, nothing will happen to the B. But if A is 1, B will be flipped. So that is the entire thing. So A is like a control line and B is like the state which will be transformed. And there is representation in terms of poly X and poly Z. So this is control Z, this is control X, which is also known as C0 gate. So C0 gate is one of the important gates. And in fact, if you see, Feynman also mentioned that in his article here. So what we call control NOT. So that's exactly what we talked about. So this is the control NOT gate, one of the important gates. But there are other gates, like some of which I've already mentioned. There's control Z, there's a swap gate which swaps the qubits. So for example, now we can already see that the control gate NOT or the CX is represented by a 4x4 matrix. This is the notation, and it's represented by a 4x4 matrix because there are two qubits. And same for control Z, same for swap. Toffoli gate, which was introduced in the 80s, I think, is double controlled NOT gate. So it's a 3-qubit gate, and there are two control lines. So instead of being just having one control line, as in the C0 gate, it has two control lines. So for example, there will be A, B, and C. So depending on the situation where A and B both are high, C will be flipped. So we can construct an equivalent table for the CC NOT gate, double controlled NOT gate. And that's an 8x8 matrix. So these are some of the gates, 1 qubit, 2 qubit, and 3 qubit gates, which are used to transform the initial states in quantum computing, digital quantum computation. So one of the things I mentioned is it's best to do some of these things by hand and really see what is going on. And for that, a lot of people in research, physics research, and other places are using something which is developed by IBM, which is like a simulator called Qiskit. And it's very simple to do this online. You don't need to install anything on your laptop. You can install on your laptop, but you can also do everything in a web browser. And I'll show you some examples. And many working codes can be found in the archive article, which I mentioned before. So let me just do a very small, show you a very small computation. So what I'll do now in my notebook is I'll just explain this and then I'll show you how it works. So I'll construct a quantum circuit with 2 qubits and 2 classical bits. So 2 quantum bits and 2 classical bits. And that is what, so it's it should be 2 here. It's not correct. So it's not 4 quantum bits, it's 2 quantum bits and 2 classical bits. And then I apply the Hadamard gate, which I explained what is in a couple of slides before, to the 0 qubit. I apply the control NOT gate, which is also known as CX gate, to 0 and 1, because remember that the control NOT is a 2 qubit gate, so I have to specify 2 qubits. And then I'll draw that circuit just to see what it looks like. And then after drawing that, what I'll do is I'll measure the 0 qubit in the 0 classical register and first qubit in the first classical register. And then I will count how many times do each of those things, how many times do I get, what state I get how many times. And for that, I'll do 1024 shots. Shots is just a term of how many times I do the measurement and what state do I measure. and then I'll plot a histogram of the counts. So let's do this. I'll just copy this and I'll write Google Colab in my Google. It'll open a welcome to Collaboratory. I'll just go to a new notebook. This is all online. I am not doing anything. I'll just paste this. I'll just uncomment this line because I want to install Qiskit, and I'll run it. And it'll just take a couple of seconds, hopefully. And okay. So there's indentation error, which can be fixed. So it will, what it'll do is it will install the Qiskit and this thing. It'll create the circuit, as I have said, and then so this circuit is going to create a Bell state. It's very easy to see that it is going to create a Bell state because if you act on Hadamard to 0, it will give you, I told you that it gives a uniform superposition, 1 by root 2, 0 plus 1. But then I do a control knot and it gives me a Bell state. So let's see. Quantum circuit is not defined. Okay, I see. Okay, I can just show you here. So if you do that, I just didn't install, so I can install it like this, but the basic idea is that if you do QCH followed by QCCX01, measure both of them, as I said, do a 24 shots, what you really get is you get 0, 0 plus 1, 1 divided by square root of 2. And that's exactly what it is. If you measure them, half of the times you get, well, you should get ideally 512. There are some errors because it's like, obviously this is noisy and it's a simulator. So if you want to increase the number of shots, if I do this 8092 or 10,000 times, it will equate to a probability of 50 and 50. So that is what it is. It is creating this state, which is a Bell state, and this is how we see. And this is the exactly. So let's just if we draw this, we can use the circuit to draw this, and it'll give you a circuit like this. So there are there are now 4 quantum bits I have initialized here, 4 and 2. And the first bit is passing through a Hadamard gate. The second bit is passing through 0 and 1 is passing through control NOT gate. And second and third are being, they are not touched. And if I do this, I create a Bell state. So Bell state is always 0, 0 initialize and Hadamard followed by C naught. So that is one of the examples which we can do using Qiskit. Okay, so this is all I've already covered both of these slides. I've shown you how to create a Bell state using Qiskit. I have shown you how to measure it such that you get 0, 0 half of the time and 1, 1 half of the time within some error, obviously. But there's something else we can do. There's a very famous state in quantum mechanics known as the GHZ state. GHZ state is an entangled state of 3 qubits. And for example, we can construct this now. So constructing this state is very similar to constructing the Bell state. So in Bell state, what we did is we did the Hadamard on 0, control NOT on 0 and 1. And for this case, what we'll do is we'll do a Hadamard on 0, controlled NOT on 0 and 1, followed by a control NOT on 0 and 2. And once we do this, we'll be able to reproduce this state, which is the entangled state of 3 qubits. There's another way of entangling 3 qubits, which is known as the W state. But you can also construct that. But the basic idea should be clear that Qiskit can be used to manipulate, construct states and manipulate them. And these are very important when we do some applications. Okay, one of the nice things about Qiskit is that it helps us to visualize. For example, as I showed in the first couple of slides about the block sphere, where we can represent a qubit, we can always represent some 0, 0, 0, 1 or some other random state on the block sphere. So this is some random state I gave to Qiskit and asked it to plot, and this is what it gives me. So as we can see that it's almost close to negative z, pointing negative z. This is very close to y-axis and things like that. So you can always visualize it and transform one state, like some state on a block sphere, to another state using the unitary gates, which we showed. Okay, so that is all fine. So till now we have seen how to just initialize the state, how to apply the quantum gates. But what else can we do? What is the physical thing which we can study? So for that, we have to go to quantum algorithms. And one of the most popular quantum algorithms, or it's not exactly quantum, it's like a hybrid classical quantum algorithm. In the NISQ era, NISQ is just like an acronym for noisy intermediate scalable quantum, is known as the variational quantum eigensolver. So this variational quantum eigensolver is a method which is now sort of a gold standard in quantum chemistry. And there are a lot of papers written about how we can compute the molecular energies of beryllium hydroxide, H2, and things like that. And this has been very helpful. So I'll just give a brief idea of this VQE in this talk. I cannot cover all the technical details, but this is a very ongoing area of research, and there are many ways to improve this, and better algorithms also exist. But for our purposes, understanding VQE, the fundamental should be good enough. So the basic idea is that we prepare the initial state on a quantum computer, that is some zero state, just similar to what I showed. For example, make a quantum circuit of some number of qubits. So it's similar to that. The first step is similar to that. Then we want to obtain some good ansatz of the wave function of the state by acting on this u, on this zero, by some unitary operators. So for example, I can start with 0 and then act on these two gates to get a Bell state. But I can also act with some random gates, some other gates, to get some other state, which might be better suited. So let's say that I act with some unitary which depends on this theta to come up with some state which is psi. Now, once we have this psi, we measure the energy on a quantum computer. It's just very similar to how we measured the state here, right? The state we measured was half the time 0, 0, half the time 1, 1, and we did the measurement here. So the basic idea is very similar. We measure the energy now on this state psi, and then optimize the parameters theta using classical optimizers. So this is where the classical part of this algorithm comes. The state preparation is on quantum, measuring is on quantum, but optimizing is not on quantum, because we don't know of good quantum optimizer algorithms as of now. So we have to use a classical backend, which is the classical optimizer, to tune this parameters theta and we repeat this process until convergence sufficient accuracy has been obtained, and then we declare that, okay, fine, we know now the wave function and the ground state energy. So ground state wave function and the energy. And this is what the basic idea of VQA is.
Sorry, may I ask you a question, Raghav?
Yeah, sure.
Okay, how do you measure the energy? Do you use phase estimation as the algorithm, or what do you do?
Yeah, I think, yeah, you can use phase estimation, but there are other fancy ways of doing that also. But you can also measure phase estimation.
Can you just say one sentence about, you don't have to explain it. I know you have a lot of ground to cover, but what is the fancy way you do? Just one sentence, please.
The fancy way you do is, so once you have this psi, you basically compute the, I think you compute the energy corresponding to that. So you basically say that, okay, what is you solve some sort of a linear equation. H acting on that psi gives you E psi, so you pull out that energy from that. You solve some sort of a linear equation, and there are no algorithms known for that.
I mean, is it a quantum? You do it quantum mechanically, right? In a quantum computer, right?
Yeah. It can be done on a quantum computer. Yes.
Okay. Thank you. Go ahead, please. Thanks.
Yeah.
Raghav, here the other question is, how do you couple this together, like the classical part and the quantum part together?
Because okay, so I think so when we can always, when we initialize and do things like that, we can always compute we can always compute some classical registers and things like that, right? So when we measure, we say that we measure the energy and then we pass it to some classical registers, and then we apply optimization methods on those classical registers. That is how it is coupled.
No, I mean, classical register, I mean, you will do the optimization in using non-classical algorithm, and that will run differently.
Yes. So there are various algorithms which are known. So once you have, so I'll show you an example. Maybe it will become clear.
Okay.
It's just up here.
Sure. Yeah. Okay.
Yeah. It will be much clearer from that. Okay. So yeah, the diagrammatic representation is this. Maybe it's also answers what Sandeep was trying to ask, and maybe Nilmani. So it's maybe I should have shown this before. The basic idea is we prepare a qubit Hamiltonian, and then we prepare an ansatz and some initial parameters. So this is like a state preparation, and then you measure the energy. You pass it through. You pass your initial state through some, and then you measure the energy on this by applying these gates, which are R1 through R2, some rotation gates depending on some phi's, and then you measure it, and then you pass it to the classical optimizer, which gives you a new set of theta values, and then you again do the same step. So you keep on doing this until you obtain some minimum value of until you obtain some desired accuracy. Okay, so one of the things which we need is the qubit Hamiltonian. We need a choice of ansatz and some initial.
Sorry to interrupt you again. Please excuse me, Raghav. Those R1 to Rn are the same single qubit gates you had introduced earlier, right? Those.
Yeah. They're single qubit rotation gates. Yes, by some angle.
I see. So you basically take your output from that first stage and you rotate each qubit with some phase.
Yes, exactly.
You measure.
Exactly.
I see.
Yeah.
Okay. Thank you.
So I can prepare some number of qubits. So for example, these can be say 4 qubits, 5 qubits, and then I apply the rotation to each of those separately, single qubit gates, and then I measure it. Yes.
Okay. I see.
Okay. Thank you. Thank you for your question. Okay, so we need a qubit Hamiltonian. Okay, that's good. So if we are going to do some examples, say for example, let's do an harmonic oscillator. What we can do is we can rewrite the Hamiltonian of an harmonic oscillator with some cubic coupling, for example, using A daggers and X in the energy representation. And then we use the fact, which is very important, that every such matrix, every 2n by 2n times 2n matrix can be written entirely in terms of X, Y, Z, and I. They form a complete basis. And these are the polymatrices with the identity. And once we rewrite the Hamiltonian in terms of these, they become something called a polystring. Polystring is just a combination of like different polymatrices and chronicled together. So for example, this method has been extensively used in quantum chemistry. This is one of the famous papers everyone talk about, scalable quantum simulation of molecular energies. But for our demonstration purposes, we just consider the anharmonic oscillator with some coupling. And this is some Hamiltonian I get. So for example, this is an 8 by 8 Hamiltonian with some value of the cubic coupling. So it's minus gx cube with some value of g. This is what we get. These are the poly strings here, identity XX and XZX with different coefficients and bunch of them together. And this, so there we can write a code which just we enter the Hamiltonian and it throws out this decomposition, and that's straightforward to do. It's given in my article. And once we have this H prime, we have the qubit Hamiltonian, and then we can take some sort of ansatz and then do the variational method. So for that, these are the basic things you can install in your Qiskit program. And this is the Hamiltonian which I just mentioned up here. So this is the Hamiltonian just represented in terms of X, Y, Z, and I. And then the step, which is the important step, is that we have to prepare some ansatz. And for that, we used ansatz which is already given in Qiskit, which is called as efficient SU2 ansatz. So you give it the number of qubits. So we have 8 by 8 Hamiltonian. So number of qubits is 3. So it will create an ansatz of 3 qubits. So for example, these here will be 3 zeros. And then, so it's a 3 qubit. So it will create ansatz for those 3 qubits. And the ansatz are made using SU2 gates, which are Rx, Ry, Rz. So in this case, we use the rotation along the y-axis of the block sphere gate, and we repeat it sufficiently number of times so the state is pretty entangled. You can remove the entanglement also, but this works as a nice ansatz. And the way we check whether this ansatz is good is like we impose the condition of some accuracy and then see what is the answer we get, because in this case we know the exact answer, so we can see what the energy we are obtaining is. Now coming back to the question which Nilmani asked about how we do the classical optimizers, and that is what is shown here. So for example, there are 2 different optimizers. They are this COBYLA and SLSQP. These are different optimization based on how you do the gradient descent and things like that. I don't know the details, and I don't want to go into the details. So this is how you do, but the basic thing is that some of the times the choice of the optimizer affects the convergence, rate of convergence and things like that. So we have to always monitor that. And how you get the energy, for example, is by running this VQE, which comes with Qiskit, which takes all this ansatz which is given to us, which is mentioned here, which is the variational form ansatz, and then we give it the optimizer. What optimizer do we want? And then we ask it to compute the minimum eigenvalue of this Hamiltonian, and then it gives us a result, and then we can compare it to the exact result, and I'll show you what we get. So let's go back to this. And so this is what I showed. This is all the routine which is being called. This is the Hamiltonian and the G use. And then the VQ result is 0.4994. Exact result is this. The error is 10 to the minus 6%. And the runtime is 1. So it's very accurate with this. But if you just change the optimizer, the accuracy changes a little bit. So one has to play around with these things, and one can also use a better ansatz, for example, to do these sort of calculations. Okay, so that is one of the basic things which people can do. The only thing we need is the ansatz and the representation of like Hamiltonian matrix, and then we can do it. But one of the things you could have asked me is that why do we really want to do so much when it's just 8x8 matrix? I can just not worry about just compute, diagonalize it right away. I mean, you can always do exact diagonalization, and at the state at which we are right now in quantum computation, most of the time when you run on real quantum computers, you can always do that thing using exact diagonalization in most of the cases, or some other fancy methods. So this is like we are not really into the quantum supremacy where the problems can only be solved by a quantum computer. Right now, the fastest classical computers with a lot of memory are almost competitive with the quantum one. But this is the thing to note is that the scalability. Once you increase a little bit of number of logical qubits or make the quantum computers better, then there is no chance for the classical computer. So we are learning these methods because once we enter the scalability region, then there's no hope of doing any ED or exact diagonalization or anything else. And in this case, you can do it, obviously, because we do it for other cases as well, but learning these methods are more important for the future and can be applied. So this is the enharmonic oscillator. I'll briefly talk about some other work done by a group in UK recently, which was interesting. So I thought to include that. We can look at O3 nonlinear sigma model, which is a very interesting model because it has a lot of properties which are very interesting to physicists, like it's asymptotically free. It has nice behavior, there's confinement and things like that. It's well studied in the 70s and the 80s. And people have also looked at scattering events in these things. So these are interesting for applications of quantum computer. The Hamiltonian is just given by the nearest neighbor interaction, the Ni Nj. And obviously, I remind you that the n square is constrained to be 1 because we are dealing with the vectors squaring to some value on the sphere. And this is the kinetic term, and we define beta as the inverse of the gauge coupling square. So what we can do is we can rewrite this Hamiltonian for some fixed dimension based on what sort of truncation we do for the angular momentum states. So for example, for the LM states which we get, you can do some sort of truncation on those states, saying that, okay, I'll only look up to L max of 1 or 2 or things like that, because the L max determines the size of the Hamiltonian on an n site lattice. So if I have a lattice of n sites, the size of the Hamiltonian is L max plus 1 to the power 2n times the same number. It's a square matrix. So this model can be studied with or without the theta term. This paper studied it with the theta term using some variational quantum eigensolver VQE methods, which I showed you. So they applied these methods to study. Now, for this case, once we rewrite the Hamiltonian in terms of qubits, so writing the Hamiltonian in terms of qubits, we can also make use of the well-known transformations, Jordan-Wigner, which you might have heard. And there's another one which people in quantum information and quantum computing also use sometimes, most of the times, is Breivik-Kitaev transformations. They are almost similar, with just the fact that the cost of Breivik-Kitaev for some physical models is much less than Jordan-Wigner. So it's much more, it scales better with the number of qubits you have. So these are the transformations you can use. Then we can construct the ansatz. So for example, right now I'm just showing you 4 qubits representation of this. We start with the 4 qubits as shown. We pass it through the RY gate, which is just the rotation along the y-axis, depends on, is given by e to the I theta polymatrix y. And then pass it through the first layer of some gates, unitary transformation, second transformation. And then we get this ansatz. And then we measure the Hamiltonian like this. This is the measurement sign of the Hamiltonian. So this is one way of constructing the ansatz. There's alternate way mentioned in this paper of constructing the ansatz. So you can be very ingenious or creative in making these ansatz, because they can affect the convergence to the exact result. So these are 2 different sort of ansatz. But what happens in this case is that both of them are almost identical. And these are the energy density. So they did this calculation using this ansatz and computed the ground state energy of O3 nonlinear sigma model. And these are the results they get. So on the left is for some value of beta, on the right is for some value, larger value of beta. And as we can see that the results for smaller beta is good, but the results for large beta is terrible, in the sense that the MPS, the classical methods, tells you that the energy should be between -5 and -6 for some truncation, and below -7 for some truncation. And whereas the VQE using 2 different ansatz, for example, the ansatz here or here, both of these, the blue and the orange, is sitting right somewhere around -2. So this is absolutely, it's not at all converging to the right answer. But for small values of beta, which is the easier regime, because the truncation effects are very less, because beta equal to 0, which is a strong coupling, is basically the trivial representation is the most important. And it's very obvious from this plot that the smaller beta are very better for VQE as well. So these things you can also do using, for example, exact diagonalization, and that is mentioned in the review. So I can do it on 4 sites, up to 5 sites, 6 sites, we can do exact diagonalization and you get the same answer. So this is just a representation of where the state of the art is. So it's still open problem to, for example, reproduce the correct energy density for the O3 model for large values of beta, which is the physically interesting regime. And probably for that, we need to come up with better ansatz or better methods and do the variational methods. Okay, so I think I have 10-15 minutes left. I'll probably go over time for sure, but I'll keep moving unless I have to really stop. So I'll just go a little quicker now. So I introduce the initial state, unitary gates, variational methods for computing and harmonic oscillator, gave an example of O3 model. But now I really come to the really important question of doing time evolution of quantum systems. So for example, for that, I would like to basically just think about a two-site model, two-site Ising spin half model, in the sense that, say, for example, the Hamiltonian is given by x cross x plus y plus y. So these are on different sites, site 1 and site 2. And this is some random Hamiltonian I just wrote down, because I just want you to convey the point of how we really do this. So it's a two-site model. The Pauli matrix is x1, y, form the Hamiltonian like this, and we want to do a time evolution of the system. So that is the real crux, interesting problem which quantum computing has to tell us about. And for that, we really want to represent this time evolution operator in terms of unitary gates. So I'll just talk about that. So if I look at this Hamiltonian and I ask the question that what is e to the minus iht, or say e to the power minus ih alpha, where t is alpha, then this is the circuit you get. And it's easy to convince that this is true. You can just plug it in Mathematica and just make sure that this is exactly the thing. It's given in the review. And I'll also show you how we can reproduce that in the next slide. But the basic idea is that we have to keep the phases small, because when we are doing these RZ alpha, alpha is the argument. We don't want to rotate by a large angle, because rotating by a large angle along some z axis of the Bloch sphere will result in errors. So we want to keep alpha small. And that is why if we want to simulate up to, say, time t, we break it into n segments of dt each, and each dt needs 8n unitary gates. So 8 gates, and so therefore n times repetition of the circuit will need 8n unitary gates. So this is the first gate, C0, H, C0, C0, H, C0, RZ, RZ. So there are 8 gates, and 4 of them are 1 qubit gates, which are H, H, RZ, RZ, and there are 4 2 qubit gates, which are C0 gates. So for this very simple Hamiltonian on 2 sides, if I want to really do time evolution properly, I have to use 8n gates, where n is the number of times I do time evolution. So if I break it in 30 steps, 240 unitary gates. So if I go to 3 sites, the cost becomes very large. And this is one of the things which is the limitation, like practically, which limits our understanding of really doing time evolution of, say, for example, of, say, if we could do a time evolution of, say, 50 spins at the moment, we could study so much from that, because we can study correlators at some given later time, we can compute scattering and things like that. But those are not feasible in the near future, at least, because the costs are, as you can see already on 2 sides, with a simple Hamiltonian like this, pretty large. So this is just a demonstration. This is another demonstration of this. So for example, in this, I showed xx plus yy Hamiltonian. What about ZZ Hamiltonian? If the Hamiltonian is ZZ, what is the circuit? The circuit is something like this. It's a C0 followed by RZ on the lower qubit, followed by C0. So there are 3 gates needed for just ZZ. And this is the initial state psi 0. And this is the final state psi t, where t is alpha by 2. And now what is alpha? Alpha by 2 is just the rotation of the argument of this RZ rotation gate. So RZ is given by e to the power minus alpha by 2 Z Pauli matrix, and this is rotation along the Z axis, and that is what t is. So if we start from here, do this, we get this. But suppose we don't have ZZ Hamiltonian, we have XX Hamiltonian. How do we simulate that? We simulate that very simply by noting that X is nothing but H times Z times H. So X Pauli matrix can be written as the Hadamard gate times Z times the Hadamard gate. So it's very simple. If I want to do X by X cross X, I just put in 2 Hadamards on the left, 2 Hadamards on the right, and stick in the same circuit as above in the middle. So if I just take this, it will give you a representation of this. Similarly, if I want to do a if my Hamiltonian is say YY, just simple YY Hamiltonian, I want to do a time evolution of that Hamiltonian. How do I do that? For that, we can use the fact that the Y polymatrix is given by S dagger HZHS, where S is this phase gate and HZH is the same X gate. So we stick in S daggers on the, there should be a dagger here, sorry. So S dagger on the left, SS on the right, and stick in the exponential of, okay. We exponential of the same thing which we saw above, and that will give us the YY, right? So this is how we can construct, say for ZZ, XX, YY. And as I already showed you, this is for XX plus YY, this is the circuit. So any poly string can be efficiently simulated by unitary gates. That is one thing. But to find a really efficient representation of using less gates, maybe you don't want to use a 3-qubit gates because they are not available. You can just use, you only want to use single qubit gates, or maybe you can use a combination of 1 qubit and 2 qubit gates. Those things need some work in the sense that you have to rewrite an equivalent circuit. But this is the basic idea of representing the time evolution of any Hamiltonian written in terms of poly strings. Okay, so this I'll skip this because I don't have time. I'll just take 5-7 minutes more. And till now, whatever I was talking about was related to the idea of qubits. It's a 2-state system, but we can play the same game using continuous variables. So there's another approach, which is the continuous variable approach. And for that, there's a different simulator called the strawberry field simulator. And the differences are here. The basic element of qubit is a qubit version of the digital quantum computing is qubits. In this case, it's Q modes. In qubit, we have poly operators like X, Y, Z, or sigma X, sigma Y, sigma Z. In these cases, we have the creation and the annihilation operators or the quadrature operators. In the other case, we have poly eigenstates. In these cases, we have coherent number states and so on. In the other case, we have phase shift, Hadamard, C0, T gate, and things like that, which are unitary gates. In this case, we have unitary gates, which are given by rotation, displacement, and other things. And these all depends on A and A dagger. So that is a basic formulation. People have studied, used this continuous variable methods or the Q mode methods to study very interesting systems. One of the simplest is the Bose-Hubbard model, which is, for example, given by this Hamiltonian. So it's on a 2-site. So I is 1, J is 2. You can rewrite the hopping term as AI dagger AJ. You can write the on-site kinetic term as this. And for that, what you can do is once you write this H as the hopping term plus the on-site term, you can use the Lie product formula, divide into n steps, and then you can approximate the time evolution using some circuit given in the parenthesis, which depends on the gates, which is mentioned here. For example, depends on beam splitter, squeezing, and things like that. So BS is beam splitter, K is what we call a Kerr gate, R is the rotation gates. And once you have this, you get a circuit like this. So for example, if I want to do 2 steps of time evolution of Bose-Hubbard model on 2 sites, this is what the time evolution circuit looks like. Beam splitter gate, K is for the Kerr gates, and R is for the rotation gate. So for example, Kerr gate is nothing but a unitary gate given by this expression, where K is some parameter. It's an exponential of IK n square, and n is the number operator. And beam splitter is just a basic gate, which is related to A and A dagger. It's like a, think about it in terms of lasers. When you pass 2 lasers through a prism, it splits the laser. So beam splitter is like that. That's why it's called beam splitter. It takes the input, and then the output is in some way split by some, depending on what phi and theta are. And 1 step of this Bose-Hubbard is given by this circuit, and we can simulate this using strawberry fields, for example. This is the code. I can just briefly go through what the code is. So it gives you the hopping transition, which is J. This is J, hopping transition. This is U, the on-site coefficient. So that is U. What is K? K is the number of the terms in the Trotter decomposition. So for example, in this case, N is just the K. So that is why it's raised to the power K. Note that if I take K to infinity, there's no error, but at finite value of K, because you're splitting this not by taking N to infinity, but some finite number, there's some error, that is K. So we define K, and then we prepare the initial state as some Fock state on a, remember that now we are dealing with photonics quantum computation, and we have to deal with Fock states. So for example, how many photons can occupy a given state? So for example, in this case, I'm saying that the zeroth Q mode can have at most 2 photons. And if I don't specify anything, it means there is no photon. So that is how you do it. And then you just introduce the gates, just like we did in Qiskit. So we introduce the beam splitter gate, K gates, and then we look at the probabilities as a function of time. For example, if I just put t equal to 0, we'll see that the probability of the in state and the out state is the same, because there's no time evolution, is the same state. But as you change the value of t, you'll see that the states are different. And that is what I'm going to show here. So for example, if I just start with this, the same code here, I just do this. But if I keep t equal to 0, like here, the probability of 0, 2 is 0, 1, 1 is 0, 2, 0 is 1, because 2, 0 is exactly the state I have created up here. But if I do this at some finite value of t, you will see that these numbers are no longer 0, but they all add up to 1. So this is the basic idea. You can play around with the code if interested, but yes. So this is the way we use strawberry fields, which is mentioned here, to do these sort of computations using Q modes. And this is what we are looking into right now with some different models. How can we understand the continuous variable quantum computation? Okay, so I should conclude by saying that we are now entering, in my opinion, and like obviously the community's opinion, a new era, which is similar to lattice gauge theories on classical computers, I would say, in the 70s and the 80s, for example. And now, once the quantum computers becomes more fault tolerant, in the sense that the errors on them go down, and they increase the number of logical qubits, we can hope to solve some problems which is difficult on classical computers. Say, for example, real-time evolution of interacting field theories. However, this is not going to happen anytime soon, since quantum mechanical principles are much more restrictive than classical computing. So it's there are many things which I've not talked about, but there are many theorems like no cloning, no deleting theorems, and the errors in quantum computers are much more sophisticated than classical methods. So we have to understand that completely, and that means that the progress might not be smooth. But for now, VQE plus other variants are sort of becoming the state of the art, and this will only improve in coming months. And with that, I thank you for your time, and I can take more questions.
Okay, thanks, Raghav, for this talk. And now you can ask your question. Anybody, if anyone has a question, please ask.
So Raghav, I had one question about your comment about tensor networks. So you said it's still difficult to go to 3D and 3+1D, etc. But like, have they been used for some 2D problems which were conventionally difficult to solve, like these triangular lattices or something of that kind?
I don't know of. Yeah, I think there are works, but I don't know of proper references. But I think some groups have applied MPS methods to study on triangular lattices and also frustrated systems. But I'm not very sure about that.
Okay.
Yeah, but if it's so you're talking about 1+1, or are you talking about 2+1?
2+1.
Oh, 2+1. No, I don't think there's anything. I don't think there's anything. No.
There's 2 space and 1 time. Oh,
No,
so even
one time, I don't think there is anything on triangular lattice and things
oh,
like
I
that.
see. Even okay,
Yeah.
going to 2 space is very difficult. Okay.
Yes, absolutely. 2
Okay.
plus 1 is like anything beyond like, yeah, 1 plus 1 is still okay, like, but 2 plus 1 is still hard. But there are methods called PEPs, projected entangled pair states. And that is kind of state of the art, but people are making progress. There are mostly European groups working on that. But I don't think they have looked at triangular lattices and frustrated systems, because that's even hard. I think it's related to the fact that when you have MPS, you can, the optimization routines and the things you use to optimize the tensors so that you converge to the like correct ground state, it works better. But when you go to higher dimension, it's like sort of the optimization problem becomes sort of non-convex, and there are other details, and that makes it really hard to do a tensor network description in 2 plus 1. So yeah.
Okay. Thanks.
Okay. Any other questions? Raghav, in VQE, is there any example anywhere that in chemistry that it has the quantum algorithm produce some result which cannot be obtained by classical algorithm?
Oh, I see. Cannot be obtained. I don't think, maybe, yeah, I don't know. I don't know exactly, but I think whatever VQE can do at the moment seems to be like possible to do like with like very large supercomputer classically also, I think.
Okay.
Yeah, because it brings us to the question of this, if you this Google supremacy on 53 qubits and things like that, right? So people, Google said that they have supremacy with 53 qubits because they can do a 53 spin system and compute the, but then someone went to a very large supercomputer in Oak Ridge or somewhere else, and they could just store 53 qubits. So it's like, I think whatever VQE can do, classical computer can do, but I think there might be some papers related to the scalable or where they have scaled it, which might be possible to do. But VQA is still not a completely a quantum algorithm. So it's not like, it's like you're comparing a quantum plus classical with classical. So it's still, you cannot disentangle the effects and other things. I think that becomes a little problematic to really
Okay.
answer whether it's really a quantum advantage. For really quantum advantage, everything should be quantum. But VQA is not everything is quantum. There are optimizers using classical.
No, that's okay. And but still it cannot give the fully classical system cannot beat the result. Yeah.
There's this paper. So there's some papers which people have written, but I don't know whether any computation which cannot be done classically has been done VQE. I don't know the answer to that. Sorry.
Like some transition matrix element or something. Yeah.
Yeah. No, I don't think yeah, people have looked into that yet. Everything VQ is mostly, I've seen on like, yeah, physics application has been really like, if there was some problem which people had looked at VQE, then it's mostly quantum chemistry problems and like molecular energies which people are doing it, mostly doing. It's not physics problem, for example, even for O3, as I showed, it doesn't work that well. But maybe there are some fancy ways of looking at that.
Okay. All right then. So if no one has any other questions, so we'll stop this talk now.
Hello.
Yeah.
Hi,
Oh,
Raghav.
yeah.
So thanks for such an interesting talk. So I had some very nice questions about the algorithms perspective. So first, like, how do we decide on the initial state, like whether it should be a 1 qubit, 2 qubit state, and how many, what decides the efficiency? And also, like, whether the optimizers, these classical optimizers can give some value on the efficiency of the ansatz used also, like whether is that possible?
Yeah, so it depends on how many qubits like. It's, for example, suppose you want to look at a 3-site model, then ideally, depending on the model, you need to have at least 1 qubit per site, right? But there are some complicated model which needs 2 qubits per site. So depending on how many sites you need, you set the number of qubits you need to basically prepare the initial state. So that is how it is determined in some sense by the system size. Let's say that. And once you have that system size, then the choice of ansatz is, there's no foolproof method of doing that. It's just like you want to try different sort of ansatz and then see what is the answer you get, whether it's like converging properly, how fast it is converging, and how many parameters or how many gates you need to represent that ansatz, because you also want to minimize the cost and reduce the error, like improve the convergence. So it's like a trade-off between convergence and the cost of the gates. So it's like that is the game you play to do those ansatz.
Okay. Thank you so much.